Semiconductors, the dance of imperfection. You know, when you think about the magic happening inside your phone, you probably imagine absolute perfection. But we're about to dive into one of the biggest, most fascinating paradoxes in all of technology. I mean, it's a wild question, right? We pour billions of dollars into making silicon unimaginably pure. But get this, the very thing that makes it work, the reason your phone can even power on, is because of its built-in flaws. So how on earth is that possible? Well, to get our heads around this, we've got to zoom way, way in, down to the microscopic level. And what you find inside that silicon crystal, it's not some static, perfect thing. Nope. It's this place of constant, frantic activity, a dance of creation and destruction that's happening trillions of times a second. And that's the key to everything. Okay, so first up, let's talk about a semiconductor's natural state. It's all about this delicate balancing act, a rhythm that physicists call equilibrium. Now, equilibrium might sound peaceful, but it's anything but a state of rest. It's this super dynamic balance. Think of it like this. You have these mobile charges, right? Electrons and their opposites, called holes, which are just empty spots where an electron could be. They're constantly just popping into existence out of nowhere. That's generation. And then, almost as fast, they find each other and, poof, they disappear. That's recombination. This generation and recombination is happening at the exact same rate all the time, keeping everything in a perfect, stable balance. And this constant rhythm is absolutely crucial. It's what keeps the silicon stable and predictable. But, and this is the big but, the real magic, the secret sauce that lets us build computer chips happens when we intentionally throw that system out of balance. So the question is, what happens then? Well, to either create or destroy one of these electron hole pairs, you've got to overcome this huge barrier. It's kind of like making a giant energy leap across what's literally called the forbidden zone. And this is where the specific material you're using matters a lot. For some materials, like gallium arsenide, making that leap is a piece of cake. It's a direct shot. But for silicon, our go-to material for pretty much everything, it's an indirect leap. This means an electron doesn't just need the right amount of energy to jump. It also needs a perfectly timed kick of momentum. It's like trying to jump from a standstill onto a speeding bullet train. It's just incredibly unlikely to happen on its own. So that lands us right back at the big mystery, doesn't it? If this whole process is so ridiculously inefficient in silicon, how in the world do we build these insanely fast processors out of it? Logically, it feels like it shouldn't work at all. And the answer, it's just so brilliantly counterintuitive. We use its imperfections. The flaws, the defects in the crystal, that's the secret ingredient. They act like little helpers, setting up shop right in the middle of that forbidden zone. Yeah, these imperfections, we're talking tiny defects in the crystal structure, a random stray atom, or even impurities we add on purpose called dopants. They create these little energy islands, and these islands are called intergap states. Suddenly, instead of having to make one giant impossible leap, an electron can just take two smaller, much, much easier hops, using these states as perfect little stepping stones. So how do these stepping stones actually work? Well, it all boils down to just 4 basic actions. A defect can capture an electron. It can emit an electron. It can capture a hole, or it can emit a hole. That's it. Just those 4 simple moves. But here's the amazing part. Out of those 4 simple actions, all the complex behavior of a semiconductor emerges. The entire fate of every single charge carrier inside that chip is decided by this sequence of these captures and emissions. And this is where things get really, really clever. Because it turns out, not all of these little helpers have the same job. Think of it like this. Is it a rest stop or is it a final destination? We can basically sort all these defects into 2 critical roles: traps and recombination centers. So you might be asking, do all these defects act the same? And the answer is a hard no. How they behave depends completely on their specific properties, especially where their energy level sits inside that forbidden gap. Okay, so a trap is exactly what it sounds like, a rest stop. It'll grab a charge, say a hole, and hold on to it for a little bit, but then it just lets it go again. The journey continues. But a recombination center, that's a final destination. No return ticket. It captures a hole, and then it waits, and then it grabs an electron, and poof! They both just vanish,
annihilated from the system. One is just a temporary delay, the other is total destruction.
And here's the really crucial part. We can control this. The dopant atoms that we intentionally add to the silicon to build transistors, they usually act as traps, as those rest stops. But other impurities, the ones we really don't want in there, like an atom of gold or copper, oh, they are incredibly effective recombination centers. They're basically the demolition crew of the microchip world.
Okay, so this is all really cool stuff, right? But if you're an engineer trying to build a new processor, you can't just guess. You have to be able to predict and control this entire dance. And for that, you need some seriously powerful math. You need a model, an equation that can tell you exactly how fast this recombination is going to happen under any possible condition. This isn't just nice to have, it is absolutely fundamental to designing every single semiconductor device in existence.
And that famous model is called the Shockley-Hall-Reed model, or SHR for short. Now, don't worry, we're not going to do the math, but the idea behind it is actually pretty simple. The top part of the equation is basically the trigger. It only kicks in when the system is out of balance. And the bottom part, that's the efficiency meter. It tells you how fast the system is going to rush back to balance, and it depends on the exact type of defects you have.
And this model gives us one of the most powerful insights in all of semiconductor physics. You ready? The most efficient recombination centers, those super effective demolition crews we talked about, are the ones whose energy levels are smack dab in the middle of the band gap. For them, location is literally everything.
All right, let's wrap this all up. What are the big takeaways here? First, semiconductors live in this constant state of dynamic balance. Second, it's the imperfections, these essential little helpers, that are the secret to making silicon actually work for us. Third, these defects can be either traps, our rest stops, or recombination centers, the final destinations. And finally, understanding and controlling this whole dance of imperfection is, without a doubt, the foundation of all modern electronics.
And all of this leaves us with a pretty mind-bending thought, doesn't it? We spend so much time and energy chasing perfection and purity, and yet our most advanced technology works only because we figured out how to harness and control its flaws. It really makes you stop and think, what does perfect even mean?